Okay, now that we understand the basic vocabulary and ideas behind vectors, we're ready to add and subtract vectors. So the I can statement for section 10.2 is I can add and subtract vectors. And we're going to start off with a warm-up question that will hopefully lead us right into what we're going to talk about today. It says, if you went 1 mile south and 3 miles east of the school, how far would you be from the school as the crow flies? So I'm going to start right here at the school, and we're going to go 1 mile south, so that would be straight down, and then we're going to go 3 miles to the east. So we're going to go this direction over here, and I'm kind of drawing this roughly to scale. And then as the crow flies, that would be this right here. It would be this direct line distance from the school to wherever we end up there. So I'm going to write down that this is 1 unit and this is 3 units. And if we just said how far is this, we recognize that south and east, they meet at 90-degree angles. So what we want to know is this distance right here. So we can use the Pythagorean theorem. So let's do leg squared plus leg squared equals hypotenuse squared. Okay, I'm using a D for that. So this is going to be 1 plus 3, so that's going to be 10. So I'm going to get D squared equals 10. We're going to take the square root of both sides. So D equals the square root of 10. And let's get a decimal approximation for that. So I'm going to go ahead and type in the square root of 10. And we get 3.162. So we're going to call that 3.16. And that would be miles. Okay, so there's the answer on that one. So from the starting point to the ending point, that would be 3.16 miles, a little bit more than 3. Kind of surprising that we had to go 4 miles to get there, but we're only a little bit more than 3 miles from the school. Now, adding vectors is a lot like these step-by-step instructions that we use to get from the school to this other destination here. So each vector is a step in the direction that you want to go. So in the warm-up, our first set of instructions took us south. So let's say we wanted to get to a restaurant and it said go 1 mile south and then go 3 miles east. So if you followed the first set of instructions, so we will call that vector A. So I'm going to put a big vector A right here. So that's vector A. When we're done with that, we're at the end of the first vector, so that we're at the tip of the first vector. Okay, and we're kind of partway there. And then if we followed the second set of instructions, we'll call that vector B. So we do vector B. We're going to end up right there. So we follow the first set of instructions here, and then we follow the second set of instructions over here. And then where would we end up? We'd end up at the restaurant right here at the end. So the result of adding A and B is the direct path. It's this direct distance right here. So I'm going to erase that D, and I'm going to write that this vector right here, this distance, would be vector A plus vector B. Okay? Now, we can actually add vectors geometrically in a couple of different ways. So we're going to talk about the tail to tip method first, and then I'll show you the parallelogram method. So with the tail to tip method, what we're going to do is we're going to take vector B and we're literally going to slide it so that it starts at the tip of vector A. So remember, you can move a vector around, you can slide it around all you want. As long as you don't change its magnitude and its direction, it's still the same vector. So what we do is we take a copy of this and we put it right there. Okay, so this is now vector B. So we kind of cross that out. And then we say the result is from the tail of the first one, the tail of A to the tip of B. So this right here would be A plus B, that little line right there. So I'm going to go ahead and erase that, and we're going to come down here and we're going to take a look at what that would kind of translate into if we described it to somebody. So what we do is we move vector B so that the tail, so the starting place, is at the tip of vector A. So that's what we did right here. Okay? And the result of the vector is from the tail of vector A, so right here, to the tip of vector B. So like this. This right here was the answer. So what it looks like on a diagram is it looks like this. Here's vector A. We start again right here at the end of vector A, and we do vector B. And that segment right there, that directed line segment, that is the vector A plus B. That's the result. Now, if you do the parallelogram method, you end up with the same thing. So take a look at this vector right here. There's the result. We end up with the same vector, but we get there differently. So what we do is we make copies of each one of these. So I'm going to make a copy of vector B. I'm going to leave vector B right there. Okay, I'm going to draw a copy of it over here, and then I do a copy of vector A. I do it like that. and then the result goes from the tail of both of them to the tip of both of them. So it's kind of like the diagonal right here. So that's what it looks like if we were to draw a picture and kind of actively do that. So we make copies of the two vectors, and then we slide the tail of each copy to the tip of the other vector to make a parallelogram, and the result is the diagonal from the tails to the tips, so the tail to the tip. And again, what we're after here is we're after this right here. That is the result, and you'll notice on both of these diagrams they end up exactly the same. So if we take a look at example number 1, it literally just says, and you've got some problems like this, it literally just says draw the resultant vector. So what do we get when we add A and B? So we take A, and to add B, you make sure that B starts at the tip of vector A, and the result would go from the tail of the first one to the tip of the second one. So this right here would be vector A plus vector B. Okay? It's literally that simple. Now we're going to come down on this next one, and it says given that u, so vector u, notice that it's in component form, is 3, 7, and vector v is 4, -2, find u plus v geometrically using either method above. Now I tend to like the parallelogram method. I think it's a little less drawing, it makes more sense to me, and I think it's less messy. So I'm going to do that one, at least for the time being. So here's the deal. Vector u is 3, 7. So horizontal component is 3, vertical component is 7. So from 0, 0 to 3, 7 here is vector u. So I'm going to label that as u. And then vector v is 4, -2. So horizontal component is 4, vertical component is -2. So that right there is vector v. Oops, and I'm just gonna leave the arrows, let those kind of speak for themselves. So I'm gonna do this using the tail to tip method. So again, we start with u. So this is our first set of instructions. There's our first vector, and I'm gonna make a copy of v. So I'm gonna slide this up here. So I'm gonna go from this tip, I'm gonna go over 4, 1, 2, 3, 4, and I'm gonna go down 2. So it looks like this. So this is the new v. See, it's still headed in the same direction, and it still has the same magnitude. So the result of u plus v is from the tail of the first one to the tip of the second one. So that would be this right here. So this is u plus v. So that's how we do it geometrically. So I've got the first one, u, I've got the second one, v, because I'm adding v to u. I leave u where it is, I make a copy of v, slide it over here, and then that's a picture of what the resultant would look like. So one of the big advantages to having things written in component form is it makes adding vectors really, really easy. So all we do is we add component by component. Component by component. And what we mean by that is we literally just take the horizontal components, we add those together, so 3 plus 4 would be 7. We take the vertical components, we add those together, and we end up with 5. We put the angle brackets around it, make sure that looks nice, and that is the answer. Now here's the cool thing. Let's take a look at this and see that it supports what we did geometrically. So this is a position vector, it's in standard form. So we start right here at the origin, and we should be able to have a horizontal component of 7, 1, 2, 3, 4, 5, 6, 7, and a vertical component of 5. So 1, 2, 3, 4, 5, and lo and behold, that's it. So we need to be able to do it geometrically, graphically, and we also need to be able to do it with component form. So on example 3, it says find v plus u. So we make sure we do it in that order, especially if we were doing it graphically. So v is 2, 5, and u is 7, 1. So the components would look like this. Let's see, we add those together, we get 9. We add those together, we get 6. So there's our answer. So part B says, confirm your answer to example 2 using component addition. That's what we did right here. Got a little ahead of myself on that one. Okay, so there's the idea with adding vectors, both geometrically and component form. So now that we know that, on the other side, we've got a little thought experiment. It says, is the magnitude of the sum of two vectors equal to the sum of the magnitude of two vectors? In other words, if you add two vectors together and then find the magnitude, would that give you the same answer as if you found the magnitude of one, the magnitude of the other, and then added them together? So maybe take a guess here and let's check and see what happens. So on this one, let's do u plus v. So u plus v in component form is going to look like this. We're just going to add the components, so that's going to be an 8. Add those components, so that's going to be a -2. And then it says calculate the magnitude of u plus v, so we're going to find the magnitude of that, the magnitude of u, and the magnitude of v. So to do this one, this should be pretty easy. This is just going to be 8 squared plus negative 2 squared. So this is going to be, let's see, we get 64 plus 4. So this is going to be the square root of 68. Square root of 68 there, okay? And then let's see, the magnitude of u. So we're going to do the square root of, this is 3 squared plus 7 squared. So that's going to be 9 plus 49. So that's going to be the square root of 58. And then this one's going to be the square root of 5 squared plus negative 9 squared. So that's going to be 25 plus 81. I think I got that right. So add those together, we end up with square root 106. So if you want to check, I think you can kind of see there's no way that this would work out. This would be the square root of 68. This is the square root of 58, so just a little bit less than that. And this is gigantic, okay? So there's no way that when we combine those together that we end up with the same result as just adding the magnitudes. Okay, let's talk about subtracting vectors. Subtracting a vector is the same as adding its opposite. So if we have vector A minus vector B, it's the same as doing vector A plus negative vector B, or the opposite of vector B. So this is just the additive inverse property at work, and we talked about that earlier this year. And that is that vector B adding the opposite of vector B should cancel out to be 0. They're exact opposites. Okay, so an opposite vector has the same magnitude, so we keep the same size, but it goes in the opposite direction. So the opposite direction. So here's what we do on a problem like this. And again, I'll show you the tail to tip method and the parallelogram method. Vector B actually has to go in the opposite direction. So vector B needs to go this way. Then we would slide this up here. Okay, so there's vector B going in the opposite direction. I've slid it around there. And the end result would go from here over to here. So there is the tail to tip method. So let's look at what that looks like in a diagram. So vector negative B would look like this. And then, like I drew up there, A minus B would be from the tail of A to the tip of B. Again, we go along this direction, then back here. And we want that direct line distance from the start to the end, so we go from here to here. That's A minus B. So if you want to do the parallelogram method, you're welcome to do that. We basically take this vector and we point it the other direction. So there's that one. We do another copy right here, and then we do another copy of A, so vector A stays in the same direction, and again, the end result just goes from the tail of both of them to tip of both of them. So here's what a diagram of that would look like. So again, here's the copy of A, going both in the same direction. Here's the copy of negative B, or subtracting vector B, and then here's our end result. So notice that this and this ends up being exactly the same on both of them. And again, just a reminder, the resultant vector goes from the tail of the first vector to the tip of the second vector. So I'm going to come down here and we're going to draw A minus B. So here's vector A, and we want to do the opposite of vector B. So we want to add the opposite of vector B. So what we're going to do is we're going to flip this around so it's going this direction right here. So this is negative B. And then we go from the tail of the first one to the tip of the second one. This one right here, geometrically, is what vector A minus vector B would look like. Okay, so that right there is the answer. That's how we draw that. Now, we're going to come down here and take a look at an example where we can graph this and have all the pieces shown. So vector U is 7, 2, so we're going to go over 7 and up 2. So we go from the origin over to there. So this is vector U. And then vector V is 8, negative 5, so over 8 and down 5. So over 8, down 5, that would be this. Okay, so there's vector V. And then what we want to do is we want to do U minus V. Now again, I told you I like the tail to tip method, so I'm going to go ahead and do that. I'm going to switch colors here. So we need to take this and we need to have it go in the opposite direction. So going in the opposite direction, let's see, instead of going right and down, we're going to go back and up. We're going to do exactly the opposite. So we're going to go back 8 and up 5. So it would look like this, okay, but I'm not going to draw it there. I'm going to draw it over here. I'm going to do a dotted version over here, but I'm going to go back 8 and up 5. So 1, 2, 3, 4, 5. Okay, so here is negative vector v. And I'm just going to put a negative there, okay? So it looks like that. So this is v. Negative v goes in the opposite direction, okay? So again, I could put a little arrow there. And then I just move negative v over to here so that it's the tip of vector u. And remember, we go from the, let me change colors here. We go from the tail of the first one to the tip of the second one. So this is the vector u minus v. All right, so that right there graphically is our answer. So let's confirm this by making sure that it works out with the components. So if I do component form of that vector, it should kind of verify what we've got. So if we do 7 minus 8, that would be negative 1. And then we do 2 minus 5, we end up with 7. So I'm going to write this right here. That's 7 minus 8. And this is 2 minus 5. So that's what we get there. So that is component form of that resultant. And let's check and make sure if this works. Again, this is in standard position. So we're going to go back 1 and we're going to go up 7, and that is where those tips line up. Okay, so we're in good shape there. And then it says just find the magnitude of u minus v. So let's go ahead and do that. Again, the cool part about this is we just take the horizontal component, we square that. We take the vertical component, we square that. So we get a 1 here, and we get a 49 here, and then we take the square root. So that's the square root of 50. And let's see, square root of 50, that is 2 times 25, and that's a pair of 5s. So this is 5 radical 2. And just for the heck of it, let's throw that in the calculator and see what we got. So we're going to do the square root of 50, 7.07. And I'm going to double check here with 5 square root of 2 just to make sure that we simplified the right way. 7.07. So we're in great shape there. That should just be, remember, we went back 1 and up 7. It should be just a tad longer than 7. So there's its magnitude. Okay, go ahead and do the self-assessment, and good luck on the assignment.